There we go. Yay! Okay, cool. So let's continue with this. So now I can say it and it will be recorded for posterity. Someday, 1,000 years from now, people will be watching my YouTube videos. So, probability, what is it about? We use something called the frequentist interpretation. The frequentist interpretation tells you what probabilities mean, like how you interpret the numbers. So for us, when we talk about the probability of an event, we're saying, if you were to keep on doing whatever random process you're looking at, like forever, an infinite number of times, after you've repeated that process an infinite number of times, what percentage of them are a particular occurrence? So in other words, what does it mean to talk about the probability that heads is 50%? That means if we were to just flip a coin an infinite number of times, after like infinity, what percentage of the coin flips will be heads? 50%. Okay? Now, I made a big point last time of these probabilities, what are they not talking about? It's like, the probability does not apply to what, you could say, because we're talking about an infinite number of repeat trials of something. Yeah, exactly. It doesn't refer to a small group of trials, and most importantly, you can't say like it applies to one particular thing. Okay, when we talk about probability, we're saying like if you were to do it an infinite number of times, this is what you would see happen. Okay, so there's this gulf between what the probabilities are about and what people usually think they're about. It's not about an individual thing. Okay, so to rectify this, we started talking about something called the law of large numbers. So the law of large numbers says, well, okay, you don't have to like do something an infinite number of times. If you were to repeat some process some large number of times, your results are going to be pretty close to what would happen if you did do it an infinite number of times, right? So this bridges that gap between, well, what happens if you don't have infinity, right? So the law of large numbers says, oh, it should be pretty close to what would happen if you were to do it an infinite number of times. Okay, and then it also says, more importantly, that as you keep repeating your process, the results should get closer and closer to the actual infinite number of times result, the probability. And then I told you about the Count de Buffon. He paid a child like to flip a coin a couple thousand times to see what would happen, right? To see if it got closer and closer to 50%. It did. Okay. So then we started talking about disjoint or mutually exclusive outcomes, things that don't happen together. So like, can you roll a 1 and a 2? No. Can you roll an even and an odd? No. Okay, so there's a nice special rule for this. If you're talking about two events that can't occur at the same time, the probability of one or the other happening is equal to the probabilities by themselves added together. So we did some examples. The good example that we did was like, what if one of them was like pick a face card, like a jack, a queen, a king, or an ace, and then the other event B was pick a 3, right? Like you can't pick a face card and pick the number 3 at the same time, right? Those are mutually exclusive. So we went and calculated what's the probability that you do either of those actions. We found that it was about 38.4%. So we calculated the probability of choosing a face card, we calculated the probability of choosing a 3, we added them together, and we got 38%. So hopefully this sort of like reminds you of what we did last time. Okay, this is like a brief recount. So today, what we're going to talk about is calculating probabilities for non-disjoint events. Oops, but let's change that to heading 2. So what if your events are not disjoint? They can occur together. What do you do then? And we're going to talk about that. So let's have our A event be that you draw a diamond card. And let's have our B be that you draw an even card. So we want to calculate what's the probability that you draw a diamond, which is your A event, or you draw an even card, which is your B event. Okay, so these are not disjoint. They're not disjoint because does it make sense that there is a diamond card there are several cards that are diamond cards and even cards? Like for instance, the 2 of diamonds, right? Does it make sense that if you draw the 2 of diamonds, event A has happened and event B has happened, right? They can occur together. Or like, the 4 of diamonds, or the 6 of diamonds, or the 8 of diamonds, or the 10 of diamonds, right? So they are not mutually exclusive. Right? Here's like the proof that those events are not mutually exclusive, because A and B occurs for both of these. Right? A occurs because all of those cards are diamonds. B occurs because all of those cards are evens. So is everyone on board with what I mean by it's not mutually exclusive? Yeah. Okay, cool. So, let's see what happens if you tried to use the rule which says just calculate the probability of A and then add to it the probability of B. Okay, this doesn't work, but let's just try it. So I'm just going to put not correct, but let's try it anyways. All right, you can't just do this because they're not disjoint. But is everyone on board with the idea of let's just see what you get if you do this? Okay, so let's calculate the probability of A happening first. So there are 52 cards. How many of them are diamonds? So of the 52 cards, remember you always do you count how many ways you can do event A, and then you divide by the total number of possibilities. There are 52 cards. So of those 52 cards, how many of them are diamonds? So, of our 52 cards, how many are diamonds? Okay, so let's talk about the cards. There are cards like the ace, the 2, the 3, the 4, the 5, the 6, the 7, the 8, the 9, the 10, the jack, the queen, and the king. You can think of the ace as a 1, the jack is like an 11, the queen is a 12, and the king is a 13. Does everyone agree that there is a diamond for each of those, right? So how many diamond cards are there going to be? Exactly, yes. So in other words, the chance of drawing a diamond is 13 out of 52, which is 1 out of 4. Okay. Now let's calculate the other probability. What's the chance of drawing an even card? Okay, now remember, so of these 13, how many of them are even? Yeah, 1, 2, 3, 4. I would just say 5 because the queen is not an even card. You can think of it as like being a 12, but it's not. It doesn't have a number value associated with it. So for each of the faces, there are 5 evens. And then how many different faces are there? 4 faces, which means how many even cards are there in total? 20, right? So the probability of drawing an even is 20 out of 52. So let's add those together. What do we get? 13 plus 52 plus 20 out of 52 is 33 out of 52. Which, if you go to a calculator, let's just plug that in. What is 33 divided by 52? It's 63.4%. So according to this way of calculating it, there is a 63% chance of drawing an even or diamond. Or another way to say it is that 33 out of the 52 cards are either even or diamond. Okay, but we're going to see, by actually going and looking at all of the cards, that this is not true. Okay. So, I'm going to take a moment and I'm going to write down all of the cards. Let's talk about diamonds, clubs, hearts. Oh my god, I can't draw a spade. How do you draw the spade? It's like... Does everyone see like my diamonds, my clubs, my hearts, and my spade? I guess instead of doing that, let's just put D for diamond, C for clubs, H for hearts, S for spades. Because I can't draw the spade very well, and the diamond just looks like, I don't know, a mouth and two eyes upside down. So we're just going to write DCHS. So let's go through and list all of our cards. You have the ace of diamonds, the 2 of diamonds, the 3 of diamonds, the 4 of diamonds, the 5 of diamonds, the 6 of diamonds, the 7 of diamonds, the 8 of diamonds, the 9 of diamonds, the 10 of diamonds, the jack of diamonds, the queen of diamonds, the king of diamonds. Yay! There's all my diamonds. Let's change color. So now I do the same thing for clubs. Ace of clubs, 2 of clubs, 3 of clubs, 4 of clubs, 5 of clubs, 6 of clubs. The 7 of clubs, the 8 of clubs, the 9 of clubs, the 10 of clubs, the jack of clubs. Oh, that's okay. The queen of clubs, the king of clubs. Okay, and then the next one will be hearts. The ace of hearts, the 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, 6 of hearts, 7 of hearts, 8 of hearts, 9 of hearts, 10 of hearts, the jack of hearts, the queen of hearts, the king of hearts. Oh my god, there's just like so many of them. And then finally, spades. Ace of spades, 2 of spades, 3 of spades, 4 of spades, 5 of spades, 6 of spades, 7 of spades, 8 of spades, 9 of spades, 10 of spades, jack of spades, queen of spades, king of spades. Yay! We've written all 52. Yeah, I know. Okay, now we're doing this for a reason. Because what are our 2 events that we're actually interested in here? So what are the 2 things that we were saying, like, hey, the probability of these 2 events happening? The 2 events are what? These are our 52 possibilities, and what are the events that we're interested in? The diamond or evens. Cool. So let's highlight all of, or let's circle all of the diamonds. The diamonds are all of these. How many diamonds are there in total? 13 of them, right? So does everyone see how I put a red rectangle around my 13 diamonds? Okay, so we were interested in drawing a diamond. What was the other possibility we cared about? Drawing in even. I'm gonna put boxes, green boxes around those. All of the 2s are evens. All of the 4s are evens. All of the 6s are evens. All of the 8s are evens. And finally, all of the 10s are evens. And how many of those do we have there? 4 times 1, 2, 3, 4, 5. 4 times 5, the 20 evens. And the 13 diamonds. So when I actually draw all of these out, what do you notice about these two different events? So hopefully you notice that there's some overlap. There are some items that show up in both of the events. And those are the things which are evens and diamonds, right? Okay. And here is the problem. If you just say, hey, there are 20 evens and there are 13 diamonds, you might just conclude that there are 33 evens or diamonds, but that's not how it works. How many evens or diamonds are there actually? So if you go through and count them, and we're going to do that, let's count them. I'm going to count them by circling them. So, like, just sort of watch for a moment. So, the ace of diamonds is 1. The 2 of diamonds is 2. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. There are actually 28 cards which are either even or diamond. These two numbers are not the same. If you just added up the number of evens and the number of diamonds, you got 33. But when you actually go and count how many cards are either an even or a diamond, you get 28. So, why did they differ is the question. Any ideas? Why did we not get the same thing? Yes. When we got the 33, you just added the groups separately, I guess would be a better word, but I get totally what you're saying. You just took the two groups and you're like, hey, 13 in this group, 20 in this group, let's add them together. But the problem is, and you used almost the perfect word to describe it, there are some cards that are in both. We call that the overlap. Or the, so let's just write that. Some cards are in both groups. Some cards are in both groups because the events are not disjoint. This leads you to double count those, if is the word. So what happens is, let's use one card as an example. the 2 of diamonds, does it make sense that it gets counted in both the even group and the diamond group? So it shows up twice if you just add up the diamonds and you add up the evens. Okay, we have a special name for that that's called double counting. Because the groups are not disjoint, if you add up the numbers, some of the cards count twice. Which is why you got 33 as opposed to the 28 that you were supposed to get. Okay. So, if you have events which are not disjoint, and you want to calculate the probability of one event or another event happening, what you're going to have to do is to count one of the events, count the other event, calculate their probabilities, and then what you need to do is subtract the chance of being in both of the groups. So A and B are the cards that are in both of the events. So these are the outcomes in both events. So as an example of this, so A was, which one was A? Sorry. A was, which one is A? My A was, oh, being a diamond. Sorry. I need to scroll up to look. Okay. So A is being a diamond. B is being an even. So how many diamonds were there? We counted it earlier. There were 13 diamonds, right? So the chance of getting a diamond is 13 out of 52. How many evens were there? 20. So the chance of getting an even was 20 out of 52. Now what you need to subtract is the probability of being a diamond and an even. So how many cards are there that are both a diamond and an even? Well, we can list them out. The 2 of diamonds, the 4 of diamonds, the 6 of diamonds, the 8 of diamonds, and the 10 of diamonds. That's 1, 2, 3, 4, 5. So this one is both. And watch what happens. These are all over 52. What is 13 plus 20 minus 5? Well, the 13 plus 20 is 33. And then what's 33 minus 5? 28, right? Yeah, 33 minus 5 is 28. And this 28 matches with the number that I counted, the 28 cards, which are either even or diamond. Remember how I went from above? I actually went and counted how many cards were either an even or a diamond, and I got 28. And that's exactly what this calculation here.
I'm gonna borrow a dress shirt.
Okay, so we'll do some more examples of this, but I'm going to pause to let people ask questions. Yeah, that's the actual percentage, because this is saying, let's just write it down. What does this number mean? It's telling you that there are 28 cards which are either even or diamond. And if you go to your calculator and say, hey, calculator, calculate for me 28 out of 52, that's 53.8%. 53.8% chance of drawing a diamond or an even. So if someone hands you a deck and says draw a card, and they say you win money if you draw an even or a diamond. The chance that you win money probably is about 53.8%, a little more than half. Okay, so what this rule does is it removes the double counted cards by subtracting this stuff. That's what this is doing. When you subtract the probability of A and B, you're removing those double counted cards. Okay. So I'm going to leave that there for a moment. So I'm going to show you a tool that will help you like speed up doing all of this. And you've probably seen it before. It's called a Venn diagram. So the Venn diagram is basically invented to speed up these sort of calculations. So we're going to do an example where we use a Venn diagram to calculate this. So one of my events is going to be drawing a heart. And my other event is going to be draw a face card. Okay, so your Venn diagram, you probably remember it. You start by drawing a square. And then you draw two circles. There. One circle. Burrito, stop. And then you draw another circle. And you want to draw them so that there's some overlap. Shh. Oh my god. Okay, I'm just gonna wait a moment for him to like tire out. Okay. So the one on the left is going to represent the events that are in A. Yeah, your dog's like, what the hell? There's another dog here. Like, can't smell him or anything. And then the one on the right will be B. And this region in here, that's the stuff that's in both of them. So we write that as A. Stop taking my shirts. Jesus. My daughter like stole one of my shirts. She's like wearing it now. Come here, show everyone. Oh, I can't really see you very well, but there she is. She's got my shirt. She's like stealing my clothes. She also has a tie of mine.
Dad, can I please go to my friend's birthday?
When?
I think at like 2-ish.
Their birthday?
Yeah. It's just like a little like meetup. I don't know.
Aren't you like in school right now?
No, I ended school like a few minutes ago.
Where is it?
I think it's at her house.
Is it in here? Around here?
Yeah, I'm not sure. We're not going anywhere. We're just gonna hang out.
Fine.
Thanks.
Alright, there we go. Okay, back to this. So anyways, there's this region that's in both of them. That's what's called A and B. That's the stuff that you would double count. Okay, so, oops. So let's get rid of, shit. Okay, let's just get rid of those little lines that I made. There we go. Okay, so the stuff in the middle, that's the A and B. The stuff that's in both. The stuff over here, that's the stuff that's only in A. And then the stuff in this circle is the stuff that's only in B. So, how many cards are hearts? How many heart cards are there? How many heart cards we got? How many heart cards we got in total in the deck? 13. Cool. So do you see how I have A with the 2 bars around it? That means how many events are there or outcomes are there in event A? So A with the bars around it, that means that there are 13 hearts. If I write B with the bars around it, that means how many face cards there are. So how many face cards are there? There's the ace, the jack, the queen, and the king. There's 4 of them, and there's 4 suits, so there's 16 face cards. Does that make sense? B with the bars around it means that's how many face cards there are. A with the bars around it means that's how many hearts there are. Now, how many things are both A and B? So in other words, how many cards are there that are hearts and face cards? Oh my god. So A and B means that they're both a heart and they're a face card. How many of those do we have? How many heart face cards are there?
No, the other one. The blue one. Are you talking about the opposite one?
How many heart face cards we got?
Let me see that one. Yeah, that one.
That's fine. No, there's not 3. There's actually, assuming that the ace is a face card, we got 4, right? Okay, so now what you do is you go fill in the numbers. In the overlap, there are 4. So I put a 4 there. Now, in total, how many things are in the B circle? In total. Yeah, it's okay. But in total, how many things are face cards? So how many are going to end up in the green circle in total? How many face cards are there? There are not 16. There are not 20. There are 16. Now, of those 16, 4 of them are also in this section, which means how many do I have over here in this leftover section? If there are 4 in that part, then there need to be 12 in here. Does that make sense? Do you see how the 4 and the 12 add up to 16? Because the region that's in the 4, the part over here with the 4, that's also in B, right? But then there's another part of the circle which is only in B, that's 12. So now you do the same thing for A. In total, there are 13 cards for A. 4 of them are in the middle, which means that you have 9 of them over here. So this helps you split it up and calculate what's the probability of A or B. So you use the formula and you say what's the probability of A plus the probability of B minus the probability of A and B. And then you go and use those numbers. There are 9 cards only in A, so you get 9 out of 52. There are 12 cards only in B, so that's 12 out of 52. Actually, my bad, sorry. I did that wrong. There are 13 things in A, so the probability of A is 13 out of 52. There are 16 things in B, so that's 16 out of 52. And then you subtract the 4, which are in both, you subtract 4 out of 52. So if you add and subtract all of that, it's 13 plus 16 is 29, and 29 minus 4 is 25. So there are 25 cards which are either a heart or a face card. So what's the chance of drawing a heart or a face card? Well, you go to the calculator, you plug in the numbers, 25 out of 52 is 48% approximately. So we can write here the 28 out of 52 means, or so the 25 out of 52 means 25 of the 52 cards are either a heart or a face card. Or you could say, well, there's a 48% chance of drawing a heart or face card. The Venn diagram, what it helps you do is like figure out these numbers. We know that A is 13, we know that B is 16, and then you get that overlap, the stuff that would be double counted. That's the 4 that we figured out. Ooh. That was sort of long. But let me see if there are questions. I'm just going to pause.